G'day, it's Geoff Currie here, and I'm just going to deliver this presentation that provides an insight into how to develop a project in artificial intelligence, machine learning and deep learning. It's not really designed for those people who have experience in the applications of artificial intelligence, machine learning and deep learning in radiology and nuclear medicine. It's really designed for those people who have a bit of an interest and not sure where to start and want to dip their toe in the water of artificial intelligence project. So I hope that provides a perspective and it meets the needs for that intermediate or beginner level. There's a publication that you can also read that provides an early introduction to the machine learning, not so much the deep learning, but the machine learning projects. Now, artificial intelligence has moved in at such a fast pace and offers so many exciting opportunities that the inclination for many people is to just jump into something big. But a more sensible and sustainable approach might be to start small, learn, build momentum, and use the internal knowledge that you're developing to then grow an artificial intelligence strategy, not only for your own research, but for the research program that you might have at your institution. So individuals or groups that are eager to build their own artificial intelligence footprint tend to target their efforts in creating world-changing, top-end deep learning algorithms. And they're very difficult and they're very expensive. The real challenge is not getting started in artificial intelligence, it's getting started without bursting the enthusiastic bubble that people have for artificial intelligence. So for example, if you consider, I guess as one example, a very keen group of collaborators who want to develop a deep learning algorithm to stratify asthma and silicosis on ventilation lung scans from disease-free scans. But they've got no artificial intelligence experience, limited funding, and to be fair, little insight into whether the lung ventilation scan has the characteristics or the features that are capable of differentiating the pathology from normality in the first place. A lot of time, energy, and money could be wasted before the project failed. Even if the deep learning provided some stratification, humans will not have learned anything because we don't understand what happened in the magic box. So for me, the first step is to determine whether there's a problem to start with and whether artificial intelligence has the capacity to be part of the solution. And the better approach would be to use the wealth of information that we have from a large patient series with known outcomes that include radiodynamic features that we've extracted from lung scans and converted into data in an Excel spreadsheet, for example, and then feed those features into a machine learning based artificial neural network. Train it on what we know with a binary grounded truth that the disease is there or it's not there. And in doing so, the artificial neural network will identify specific inputs or features that individually or collectively provide the highest predictive capability for disease. It may reveal that the lung scan plays an important role, or it may reveal that it plays no role at all, but you haven't wasted time and money with the deep learning to uncover that. So in the case of the artificial neural network and machine learning showing that the lung scan plays an important role, then what that does is it actually provides justification to then move into a deep learning and convolutional neural network process. And it might even provide justification for funding for the same. But in the case of the latter, that you've actually avoided wasting time, wasting money, and avoided going down that deep learning pathway and move on to another project. So for those that are considering projects in artificial intelligence or trying to create a footprint for yourself or your department, a few dot points to think about to get started. Consider a problem where the solution provides a really good outcome and quickly. To use that momentum to have an early win and build not only success and a footprint in AI, but also interest from other people in what's going on in your artificial intelligence environment. Avoid taking on high investment, so projects, so things that require a lot of time, a lot of resources, a lot of energy, you can burn that out really quickly, and in particular, a lot of funding. So if you need a lot of funding to get a project started, you may not get it, particularly if you don't already have an artificial intelligence footprint. If it's dependent on that funding, well, then it just sits idle and never gets done. So avoid those high investment projects that provide no reward for a long period of time. You're just going to burn all your energy and your interest. You need those early wins as per the first dot point. Ensure the outcome's not trivial. So there's a lot of projects that are very successful around artificial intelligence, machine learning, and deep learning. But people go at the end of it, they go, well, so what? You know, like you show that it works, but you know, it's not going to change practice. It's not going to change what we do because the results are trivial. So think about the outcome itself is going to have an impact. It's not a trivial outcome. It's something that people can use. So it addresses a problem that has that impact and will generate further attention with success. And that then drives enthusiasm and energy and time and money and all those other things. Focus your efforts on projects that tangibly connect to radiology or nuclear medicine rather than peripheral areas of interest. Now, you know, tangibly connect could be some of the business practices that we do, but if your project is purely built around image recognition and you're using non-medical image data just to prove that you can do something, then you're probably not going to generate the internal interest and funding that you might think. Ensure your team is comprised of credible colleagues internally and externally. And if that means recruiting the right people, then do that, build those collaborations. So what's really important is to say, well, I don't have all of the expertise, so who do I need to fill those gaps? And make sure you actually get people that share your level of enthusiasm and your level of trust with collaborating in research. It's like building any other collaborative relationship. So recruit a team that's comprised of complementary skills. You don't all, if everyone's thinking the same and everyone has the same skill set, you're not going to get the project done. You want people that actually look at the problems differently, that bring different and complementary skill sets to the project so that it drives enthusiasm as well as having those capabilities that can accelerate both the project and the resulting momentum on the other side. So how do we go about developing a project? So when we develop a artificial intelligence strategy for your research team or your department, it's not an overnight journey. Don't expect that an exciting project convolved today in the tea room discussion to have a clinical impact anytime soon. You need to consider things like the scenario where a data-rich department, you might be a data-rich department, that can train an artificial neural network or a convolutional neural network to perform a particular task, and then validate that algorithm can occur fairly quickly. So this scenario represents almost all of the current literature that's available in radiology and nuclear medicine. So when you're actually looking at what's available in those journals, many of them are just validating, building, training, and validating testing those neural networks. They're not inference stage. They're not actually applied to the actual real world. And so when you look at the number of FDA approved algorithms that are being commercialized, it's a very small list. It's a very short list. And so even though you might have an internally valid project or an internally valid algorithm that's driven on your internal data and had success with your training and validation, provides an algorithm that can be reliably perform the prescribed task within your internal environment, but it may not have that external validity. So the process to get it externalized and commercialized is a much more difficult proposition. So consider, and I know this is a nuclear medicine scan, you could do the same thing for a CTPA or similar. It's a very simplified image because it's only got one ventilation and one perfusion image rather than the whole set of data, and typically we would do it as a spec study. So it really is an oversimplification just to make a point. But you can see that what I've done is I've displayed the ventilation, the perfusion scan, and then two things. The first thing is a defect probability that's driven by your deep learning algorithm. And so on the ventilation scan, it identifies that it's improbable that there's a defect. So it's just a color-coded risk score or a risk of a defect existing. And then on the fusion scan, you can see that there's a couple of areas where there's a high degree of certainty in red that a defect exists, and a few probable areas of defect as well. And so that's a nice, easy way of demonstrating not only the defect risk probability, but also highlighting visually where the algorithm is seeing or looking at in terms of defects. So that could be then correlated back. And then based on that defect probability, providing and the defect probability difference between the ventilation and the perfusion, you could then actually generate a numerical score that's based on the probability of the patient having pulmonary embolism. And that would be a really neat way of summarizing your deep learning outcome. And this is just another mock-up that, and there's a couple of sites that have actually done something very similar to this that are not a mock-up, but actually for their patient database. And so looking at a bone scan, a whole body bone scan is someone that's looking for a metastatic spread of breast or prostate cancer. In this particular case, it's a prostate cancer patient. And the auto segmentation of the artificial intelligence algorithm using a convolutional neural network identifies normal tissues, so green being bladder and kidneys, identifying non-normal bone uptake, but not just non-normal bone uptake, but also identifying the intensity relative to what it had learned is normal in the training phase, and giving those color codes based on suspicious versus highly suspicious weather versus something that's relatively certain. So you can identify the degree of certainty around metastatic lesions, but also to then roll all that together to provide a cumulative metastatic burden score. So we need to roll on from there and start to think about how we would actually start to work all this together. And to work out a project, particularly for deep learning, we need to start to think about the code that we use, the frameworks and the libraries that we use. So this is just a schematic representation of the relationship between our hardware in the outside with the green. So you need a CPU, but you need a GPU or a TPU, so a graphic processing unit or a tensor processing unit to be running your deep learning algorithms. The frameworks and the architectures, the libraries that feed the tools that we actually use, the databases themselves to provide the deep learning solution, and of course the language that you use is Python. So this is geared for Python. So we've got PyTorch and NumPy and other TensorFlow and Keras feeds into Python language as well. So let's talk about Python. Python is a high-level open source code. It's fairly simple. It's intuitive programming language that can be used for direct coding of machine learning and deep learning, or the source code for things like Keras, a base network development. So that's an application training interface. It's not the only programming language used for artificial neural networks and convolutional neural networks, but it's probably the most common, and certainly it's the most accessible and usable for those early developers. NumPy is an extension package for Python that allows algebraic functions, Fourier transformation, integration of Python code with other codes like Fortran and C. It's a little bit like the scientific calculator being added to a standard calculator. So in effect, it adds that degree of functionality, and you'll see where we actually integrate it in when I show you some code in a few minutes. So we should look at frameworks and libraries, and I've provided all of the links to the various websites that you can download these resources. So Keras is a deep learning library that runs as an application programming interface for Python in conjunction with TensorFlow. PyTorch is an alternative open source library of tools for training phase platforms. TensorFlow itself is a graphics-based computation platform that stores data as objects or tensors rather than integers or strings. It's used as a back-end platform for convolutional neural network development, but it can include Keras for broader applications in training phase of the process. So the framework itself and associated libraries might be described as the ecosystem, while the architecture and databases are the landscape. And I use those terms throughout other presentations. So CAFE is the University of California, Berkeley's deep learning framework, and is useful for those that are a little bit more adventurous with their deep learning research. CNIME is a deep learning analytics platform for convolutional neural network development, training and implementation, and integrates with Keras deep learning architecture and also with the TensorFlow machine learning library. Theano is a similar library for, like a scientific extension of the Python, similar to Python and NumPy, where it adds the scientific calculator. So it's like a scientific extension to these packages, in particular Keras and TensorFlow, with the additional features associated with optimization and speed. And then there's other things like deep learning, 4J. It's a Java-based open source deep learning library that can be integrated with Keras and Python. There's Pandas, which are powerful data analysis toolkits that are used for Python code. So essentially it's a library of tools for those using Python for data analysis. And this is just a very short list of what's available. So let's look at a deep learning example. A useful starting point for exploring the convolutional neural network and the deep learning is using commercial development environments. So rather than actually trying to program AlexNet or GoogleNet yourself and trying to learn the code, then what you can actually do is use some of the development tools. So there's numerous tools that are available, but there's two that I'm going to recommend here. The first one is the MATLAB Deep Learning Toolbox from MathWorks, which is useful software program to develop and deploy convolutional neural networks for the novice. And you've got the web address there, and that's downloadable onto your computer. It's useful on your computer to make sure that you've actually got a TPU or a GPU. And the gaming computers. So just if you wanted to do some deep learning things on your own computer, you need some speed about it. So you got some neural processing networks on some of the newer computers. But if it's a computer that's set up for gaming, then it's going to have a reasonable sort of a GPU and processing tool. So those gaming computers tend to be good or okay for desktop deep learning applications. So the second tool is the CoLab, which is obviously short for Co-Laboratory, which is a convolutional neural network development environment that uses Python language with TensorFlow. And basically it's a platform that allows the code to be developed, run, and shared via Google Drive. So in this particular case, you can be operating with a standard computer with a CPU, no GPU, no TPU, because it actually runs from the Google Cloud, and there's no cost, it's free. So it runs from the Google Cloud, and it actually uses their GPU and TPU. So it means that you've got more powerful tools at your disposal without the cost. So CoLab makes some of the more time-consuming configuration processes also more streamlined, because it's almost like a graphical user interface that you put in your parameters and it does the programming behind the scenes for you. And so this avoids the need to configure your own computer with the tools for code development and implementation. So that brings us to the end of a very brief presentation. Really, it should be about an hour or so presentation that gives some worked examples of how you would use different tools and different code to produce a machine learning or deep learning project. But as a beginner step to give you a bit of an idea of what some of the challenges and some of the tools that you might use, then it's actually a pretty good start. But more than happy to chat again at another time and give you some richer insights into the actual applications in terms of the code. So some Python coding associated with some of the neural networks, some worked examples of machine learning options, and I can even work you through the code associated with a Colab project, for example. But for now, we need to just sit there and think about how artificial intelligence, machine learning, and deep learning have an array of applications for nuclear medicine and molecular imaging and radiology more generally, and think about how those things might work. We need to think about that there's, generally speaking, a lot of narrow scope that's been in the literature. Think more broadly about how you could potentially problem solve in your department using machine learning or deep learning. It's important to identify problems that are fairly, immediate and have tangible benefits. So by solving those, that you're actually using machine learning or deep learning as a tool to solve a problem that has a tangible benefit, an immediate benefit to your department. In many cases, problems don't need artificial intelligence, machine learning, or deep learning. So don't overdo it. So don't overcook it. Don't try to jump into a big machine learning project or deep learning project when really you don't need those tools to solve the problem. Just find the simple solution. And so the most logical approach to developing any problem or project would be to start with machine learning. So think about the problem that you have. Think about how you could use machine learning to get richer and deeper insights into the problem. And then when you've got those richer and deeper insights, then start to think about how a deep learning approach might actually give you a more definitive outcome. So it's sort of a stepwise approach. Sometimes you don't need deep learning. And machine learning certainly allows you to make a more informed step into the deep learning arena. So that's all I have. Thanks for listening. If you have any questions, or comments, or discussion, you can hit me up on social media, or my email address is gcurrie, GCURRIE, at csu for Charles Sturt University.edu.au.